So first of all, you can simplify, and because these are just parabolas and cubics, the integral is easy on both sides. And then we can find the area of each section separately, add them up, and we get our total area. Thank you. You're welcome. So the difficult part here would be the sketch of the graphs. Because without a calculator, what would you have? You would have to know that you've got a parabola, that's fairly easy, and this parabola opens up, that's fairly straightforward as well. You find your intersection points, and you find out that there are 3 of them. So having 3 of them has this kind of situation. So with the cubic graph, how would I go about solving or graphing this cubic graph? Well, you could factor out the x squared out of the graph, giving me 2x intercepts. So on our cubic graph, if I knew these were 2x intercepts, and I know it's a positive cubic graph, that it has to start down here and end up here, that gives you this as an idea. You might use some of your grade 12 pre-calculus for this. Because x squared has a multiplicity of 2, it bounces at that x-intercept. But you could also use your calculus to help you graph it too. It just depends how much time you want to spend getting ready for this question. Now if we had our calculator, you could type these equations into your calculator. You could type 1 into y1 and 1 into y2. And so you could simplify it and type it into your calculator. But another option would be, and I'll put my calculator here, is that you could type 1 into y1 and 1 into y2. So I'm going to just show you a little bit of that and how we could use it. We'll get one of these answers. And as it says here, this is way faster, but not as exciting. Okay, I'm going to steal the equations from here. X cubed plus 2x squared. So if I go to my y equals, how can I do this faster? I can clear this out, clear this out, and clear this out. And in y1, I'll put the x cubed plus 2x squared. And in y2, I'll put the x squared plus 2x. So there we get our graphs. And if I want to find the integral between, so I'm going to go to math, go to my integral number 9. I'm going to find the integral between -2 and 0. And in that first situation, we look at the graph, the x cubed graph was on first. And I had put my x cubed graph into y1. So on my calculator, I can, in here, choose y1 minus y2. And of course, you're still differentiating with respect to x. But because y1 and y2 were equations with x, this should and will give me my 2.667. I can change that to a fraction and get my 8/3 exactly like we did before. So your calculator, super helpful. On your first take-home quiz, we're going to get you to show all of your algebra and mental math for each of the multiple choice, because you can get almost all of the answers quickly, cheatingly, with the calculator. Well, I still want you to use your calculator to check that the answer is right, but I do want to see, and we're going to ask you to show all of your algebraic steps for each of these as well. But it is nice to know that the calculator finds you the answers very easily. So you saw we got the 8/3. We could have done the same with the second part and added those two parts up together. Find the area of the region bounded by the graphs of sine x and cos x, and have their point of intersection. So from your unit circle, you know that sine x and cos x are equal at pi over 4. So we have the point pi over 4 comma root 2 over 2. I'll make that more legible. Oh, look at that. Such a nice video so far.
Oh, you're on mute?
Well, it doesn't look like the light's working at all. So Neela will just have to get all the information from quietness for the first bit. And now we're back online. All right.
My speakers are broken.
Yeah, we probably turned it really loud, realized it didn't work, and now it's just copying down the notes, and then in the middle of it, at this moment, it's going to get really loud. So then our area, the cos graph is above, the sine graph is below, and now we've got integrals that we can do. The integral of cos is sine, the integral of sine is negative cos. And as an exact answer, that area is root 2 minus 1. So here's an example. If we used our calculator, you would get a decimal answer that doesn't change to a fraction, and then that probably wouldn't be helpful on a multiple choice question on the exam.
Is this in the wrong place?
No, it's good. I'm just getting excited about the next section. So the next section, we're going to do the same idea, but we're going to imagine that the person who started off mixed up their x's and y's. Would it make it any different if you wrote y instead of x and x instead of y, and you labeled your y-axis x and your x-axis y? It would be confusing for you for a little bit, but it's just variables. So what we can do is sometimes it's easier to find the area of the curve if you think sideways and look at your y-axis than if you think normal and think of one function above the other. So now we're going to think of one function above the other, but farther to the right than it is on the left, and we can find the area between those two curves. So when you're doing the x's, it's the above curve minus the below curve. And if you're thinking about doing it the other way and using your y-axis, then you're going to do the right curve minus the left curve. I go back? There we
Oh, we were supposed to break that.
go. Oh,
We were on my pencil.
there we go. Don't even have a pencil anymore.
I just took a bath in my own water. It's really good. Oh yeah.
All right, we're good? So here we have two equations. One of them is a sideways parabola, x equals y plus 1 squared. And the other one's just a straight line, but we've rearranged that straight line. Instead of being y equals mx plus b, it's x equals. You could do that anytime you like, right? So the difference here is that we have the x by itself, where we normally have y by itself. But in a sense, this is just like solving a question where you had y equals an x and they just switched the variables. But now we've drawn everything sideways. Okay? Like if you had written y equals x plus 1 squared, can you see that would be a parabola? And you just have to take your paper here and rotate it and flip it around, and then it would look exactly like we've done before. But now that we're dealing in this direction, we're going to say I can find the area. When I find the area under a curve on my y-axis, for example, on the red graph here, which is the one farthest to the right, now I would figure out all of this area. When I'm thinking area under a curve, it's now area towards the y-axis under the curve. Can you still see under the curve but sideways? So what we're going to do, just like before, I lost my it's not colored in as nicely as before. We're still going to find our intersections. So where do these equal? They're equal at y equals positive 1 and negative 1. You could find the points exactly, but not necessary. You just need the y values. And now our area there, by partitioning the y-axis, now we would have a dy instead of a dx. And we take the curve on the right, which was the line, subtract the curve on the left, which is the parabola. Simplify and evaluate. Now, in this example, had you wanted to, it would have been easy to get this y by itself. You'd have to move the 2 over and get x minus 2 and then divide everything by 2. You could get y by itself in that equation. And same thing with the other one. If you had square rooted both sides, you would get y plus 1 equals plus or minus the square root of x, and then subtract the 1 on both sides. And that one has the plus or minus, which is two square root graphs. You would have, from this point here, one square root graph, which would be this one above, and one square root graph, the negative one would be this one below. And so had you wanted to, we could have found the area between these two curves by using, and I guess since it's the positive one, you could use the square root of x minus 1 as one equation, and your line here as your second equation, and you could partition the x-axis and say you would now go from area between 0 and 4 and do the square root graph minus the other graph. But because it doesn't matter which variables are where, having the x equals, we can just think of the same thing, just doing it in the opposite direction. And really, if you had wanted to, you could even do this same thing by redrawing it with your x and y axis split, but we won't do that. So it's just kind of neat to see that you can either find the area between the curve using the x-axis with a dx or a y-axis with a dy. Here's another one. Both of them are already x equals, so it makes more sense to partition the y-axis. We need to find out where they intersect, and they intersect at -2 on the y-axis and 1. So now, if you're partitioning the y-axis, you want to use the y-coordinates. The one further to the right is the parabola. The one further to the left is the line. Subtract them, integrate, and we can find our area. Go back to the first part here. So sometimes we have options. You can either decide to split things up with the x-axis or split things up with the y-axis. This is a good example because the equations that are given, one of them is y equals, and when it's y equals, usually you do separate the x. And one of them is x equals, and that one you usually separate the y. So now we have a choice. Which way do we want to separate it? Okay? So we want to find the area between the graphs, but we also want to find the area between the graphs and the x-axis. So only this purple shaded part there. So if we decided to do the x-axis, we would have the following situation. I would, from 9 to 1, the red graph doesn't come into play. So from 1 to 9, I could just do the area under the curve of the blue graph. And then from 0 to 1, I would have the blue graph minus the red graph. Well, what does that look like? First of all, we would need all of our equations in y equals. So this second equation, that is, you would have move the y squared over, and you would get 9 minus x. You would have to square root both sides, and you would get y equals plus or minus the square root of 9 minus x. And of course, which one are we looking at? We're only concerned about the one that's above, so that'll be the positive one. So between 0 and 1, we have the one graph minus the other graph. And between 1 to 9, you just need to have 9, the area under the curve of the square root of 9 minus x. I'm just going to put a red box around that equation so that you realize that that's connected to the red graph, and a blue box around that equation so that you see that that's connected to the blue graph. An x equals y squared graph will always give you a sideways or a horizontal parabola. So now from here, we just need to evaluate. We can separate these ones. If you wanted to, when you separate things out, you notice that you've got from 0 to 1 of 9 minus x, and then 1 to 9 of 9 minus x. Putting those together, that's just 0 to 9 of the square root of 9 minus x. By putting them together, it just means you have less algebra to figure out, or less mental math to do. So that can be helpful. Anyways, the rest of this, plugging in numbers, fairly straightforward. And so when you get a final answer, I always love these answers where you take strange shapes like parabolas and your final answer doesn't even have a fraction in it. It's crazy. Hopefully she read her email and doesn't yell at me. She does, just take it in. Very nice. Okay, now we're going to look at doing the same thing, but with partitioning the y-axis. So at the y-axis, you're doing the right curve minus the left curve. And what we're going to need to do is we're going to need to make both equations x equals. So the one equation was y equals the square root of 9 minus x. You would have to square both sides and get the x by itself. So our preliminary work is now to make both equations x equals. And we have to take the equation on the right and minus the equation on the left. Now this was the blue one. And this is the red one. Technically, there is a restriction on the red graph that y is bigger than or equal to 0. Because when you square both sides, and what I wrote, when I have this x equals negative y squared over 9 plus 1, technically, that's another sideways parabola which would have that bottom part. When I change it to x equals, technically I should have this restriction on the y values to show that it's only equivalent for those values, or you could say that x had to be less than or equal to -1, but for this question, if that wasn't there, that you would have no deduction because of the way the equation was written originally. So now we just take the 1 on the right minus the 1 on the left. The nice part about partitioning the y is you didn't have to think about two different sections. When you partitioned the x, part of it, we had to only consider one graph, and then the other little part, we had to do both graphs. Partitioning the y, you can just do the right graph minus the left graph. And luckily, we got the same answer. So again, this one you could do both ways. I like partitioning the y better, but you have to sort of consider what is everything you have to do. So first of all, if I would look at this one and I would decide, am I going to partition the y-axis or am I going to partition the x-axis? These are the kind of things you need to consider. Maybe there's one that you like better. Most people like partitioning the x-axis better because they've done more questions with that than partitioning the y. And so if that's the case, you might choose that you partition the x, and if you partition the x, you have to consider these two different sections. That to the right of 1, it's just the area under the blue curve. But between 0 and 1, then it would be the blue curve minus the red. If you feel comfortable with both partitioning the x-axis and the y-axis, in this situation, you might consider, hey, if I partition the y-axis, I have a graph on the right and a graph on the left for the whole thing. So that might make it easier and less work for me to do. Other things to take into consideration when you look at the original equation. If they were both already y equals, then it would probably make more sense to partition the x-axis. But if partitioning the x-axis made you have to break it up into a bunch of little parts, it might be worth the time to change them all to x equals. So these are some of the problem-solving things that you can do in questions like this. All right, Chuck. Yeah, I'm going to start a new video.